graph the quadratic function f of x is x squared minus 4x minus 4 by plotting points. Now let's look at the domain and range. So if I plot the point -5, and I put -5 in there, my function is 1. And you can plot pretty much any point you want, but you need enough to give yourself an idea of what the graph's going to look like. And when I graph the points, I see I've got this curve here, connect them with a smooth curve. Giving the domain and range based on what I have here. And you do have to be careful when you're plotting points that you have enough points to get the maxes and the mins, vertices in there. The domain for a quadratic is, of course, all real numbers. And the range is going to be from -8 to infinity. For polynomial functions of degree n, f of x is equal to a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus ... Now we're going to leave out a whole bunch of terms, so we're going to do ... plus a1x plus a naught, where a sub n minus 1, all the way down to a1, a naught are numbers. They can be complex, but a sub n can't equal 0. Usually, our complex numbers are actually just going to be real. So make sure you know the function types. A polynomial of f of x is equal to 2, or f of x is equal to any constant. This is a constant function. The degree is 0 because this is really what? Times x to the 0. And the leading coefficient is 2. For f of x is 5x minus 1. This is a linear function. The degree is 1 because there's really a 1 there. And the leading coefficient is 5. For the quadratic function, the degree is 2 because that's the highest power. And the leading coefficient is 4. For the cubic function, the degree is 3. And the leading coefficient is 2. In this example, this is a quartic function. Now, this is an ugly number. It's okay that it's a square root of 2, but the highest power is 4, and the leading coefficient is 1. There's an implied 1 there. For the quadratic function, all right, f of x is ax squared plus bx plus c. The domain is from negative infinity to positive infinity, and the range is from 0 to infinity. In this example right here, f of x is x squared. So a is 1, b is 0, and c is 0. To graph quadratic function, we like having it in this is called vertex form. F of x is a, x minus h squared plus k. The a is my leading coefficient. It points up if a is positive, down if a is negative. If the absolute value of a is greater than 1, it's going to be a vertical stretch, while if the absolute value of a is between 0 and 1, it's going to be a vertical shrink. Horizontally, you're going to have this x minus h. You remember, if h is positive, it's to the right. If h is negative, it's to the left. The plus k is your vertical shift. If k is positive, it's going to be a vertical shift up. If k is negative, it's going to be a vertical shift down. So graph y is negative 2x squared and compare it to y is x squared and y is 2x squared. Now, the graph of negative 2x squared is a narrower version of y is x squared, and it's reflected. You have that negative right there. So if I were to graph each of these, the red one is, let's see, now the green one is y is equal to x squared. I have to be careful here. All right, so y is 2x squared is vertically stretched. And then y is negative 2x squared is a vertical reflection of y equals 2x squared. So the domain of each of these is all real numbers, and the range of g of x is negative infinity to 0. So if I were to graph y as negative 2x plus 3 squared plus 5, um, I would see that this is translated 3 to the left and 5 units up. All right, so this is my original equation. So it's vertically reflected and stretched, but then we're going to take it and move it to the left and move it up. The domain is still all real numbers, but in this case, the range is from negative infinity to 5. Now let's review the technique of completing the square. Suppose f of x is ax squared plus bx plus c. The first thing you're going to do is factor this leading coefficient a out. Now you're going to notice when I take a out of ax squared, I'm left with x squared. When I divide a out of bx, I'm left with b over a times x. You see all this empty space? You're going to want to leave that on your paper. And then plus c. So you remember when we complete the square, we take the middle term, this b over a, divide it by 2, and square it. And so we add that in, but what we add in, we also have to subtract back out. So that was why you needed that big space there. The next thing you're going to do is distribute the a and rewrite it. So this part right here is a perfect square. All right, x squared plus b over ax plus b over 2a squared is x plus b over 2a squared. Remember our perfect squares. Now we're going to take this a here, and we're going to distribute it to this second part right here. So it is negative a, because you get the negative from right there, negative a times b over 2a squared. And then don't forget your plus c. We can rewrite this in standard form as a x minus h, where h is equal to what? B over 2a plus k, where k is this, kind of ugly, c minus a times b over 2a squared. Now you'll be doing this with numbers. You won't be doing this with symbols. So suppose I wanted to graph f of x is x squared plus 2x minus 5 and find the largest open interval where the function is increasing and decreasing. Well, the first thing you want to do is complete the square. A is already 1, so I don't need to factor it out. So I'm going to take this middle term 2, divide it by 2, and square it. So I'm going to add 1 and subtract 1. Next, I'm going to do grouping. So this right here is my perfect square. And I'm now going to have those two as my constant terms on the outside. So this becomes x plus 1 squared minus 6. So I see that this is a horizontal shift to the left 1, then a vertical shift down of 6. I have a vertex at negative 1, 6, and an axis of symmetry at x equal negative. Now, let's find additional order pairs so that we can give it a nice graph. If I pick the points negative 3, I get negative 2. Negative 2 is negative 5, 0 is negative 5, and 1 is negative 2. And if I graph my points and make a smooth curve, I see that the function is decreasing from negative infinity to negative 1, and it's increasing from negative 1 to infinity. So now, what if I want to graph this, and now I want to identify the intercepts? So the first thing I need to do is complete the square. To complete the square, I'm going to factor 2 out of these first two terms, and then I'm going to bring my 6 down out here. I need to look at my middle term, divide it by 2 and square it. So 1/2 divided by 2 is 1/4. 1/4 squared is 1/16. So I'm going to add 1/16 and subtract 1/16. Now these first three terms are a perfect square. So this is 2 times x squared plus 1/2 x plus 1/16. There's my perfect square part. Plus 2 times, you remember we have to distribute this to this negative 1/16, minus 6. Rewrite this as a perfect square, 2 plus 2 times x plus 1/4 squared minus, when you add all this together, you get 49/8. So I have a vertex of minus 1/4 minus 49/8 and an axis of symmetry of minus 1/4. So you graph your vertex and you pick points on either side and pick numbers that are nice, especially if it's a fraction. Pick numbers that are going to give you nice answers. Now, when you graph quadratics, remember that any quadratic of the form ax squared plus bx plus c can be written as f of x is a, x minus h squared plus k. The vertex, the x value of the vertex is minus b over 2a. And k is the y value evaluated at h. So you can always find the vertex from this equation. The graph has the characteristics of a vertex of hk and an axis of symmetry of y of x equal to h. When a is positive, it opens up. When a is negative, it opens down. It's wider than the graph of y equals x squared when the absolute value of a is less than 1, and it's narrower when the absolute value of a is greater than 1. The y-intercept is just going to be when x is 0, and then when f of x is 0, of course, it's c. So the y-intercept is 0, c. The x-intercept can be solved by using the quadratic formula, ax squared plus bx plus c is 0. When b squared minus 4ac is positive, then the intercepts are going to be minus b plus or minus the square root of b squared minus 4ac all over 2a, comma 0. When it equals 0, the x-intercept is minus b over 2a, 0. And when the discriminant here is negative, then you don't have any x-intercepts at all. So find the axis and vertex of the parabola having the equation f of x is minus 3x squared plus 12x minus 8 using the vertex formula. Well, a is negative 3, b is 12, c is negative 8. So the h value is minus b over 2a. So it's minus 12 divided by 2 times negative 3. So the vertex is x is equal to 2. So the axis of symmetry is x is equal to 2. The vertex is 2, f evaluated at 2. So I'm going to substitute 2 in for x. And I get f of 2 is 4. The vertex is 2, 4. Now suppose a ball is projected directly upward with an initial height of 75 feet with an initial velocity of 112 feet per second. Give the function that describes the height of the ball in terms of the time t. Now remember, the projectile function, we're doing with feet, so it's minus 16t squared plus v naught t plus s naught. So you're told that v naught, the initial velocity, is 112, and the initial height is 75. So my equation is minus 16t squared plus 112t plus 75. After how many seconds does the ball reach its maximum height, and what is the maximum height? We're looking for the vertex. The maximum height is going to occur at the vertex. So a is negative 16, b is 112. So the vertex occurs at minus b over 2a, or negative 112 divided by 2 times negative 16, or at 3.5. What is the maximum height? I'm going to need to plug 3.5 in my equation. So y is negative 16 times 3.5 squared plus 112 times 3.5 plus 75, or 271. So the ball reaches its maximum height of 271 feet after 3.5 seconds. If you were to graph this on a graphing calculator, then lo and behold, there's your maximum. For what interval of time is the height of the ball greater than 200 feet? So this is an inequality. Solving this, I have negative 16t squared plus 112t minus 125 has to be greater than 0. So let's use a quadratic formula to solve this one. A is negative 16, B is 112, C is negative 125. So T is 1.39 or 5.61. Now let's choose two numbers and divide the number line into three regions and use our test values to see when this is true and when this is false. So from negative infinity to 1.39, if I put in 0, I get a false statement. From 1.39 to 5.61, if I pick 2, I get a true statement. And from 5.61 to infinity, if I pick 10, I get a false statement. So the ball is going to be greater than 200 feet between 1.39 and 5.61 seconds after it's thrown. Now, after how many seconds will the ball hit the ground? So we're going to want to know when it is back at S is 0. So we're going to use a quadratic formula to find the positive solution of negative 16t squared plus 112t minus 125 is 0. I'm going to get two solutions. One is negative 0.62 and one is 7.62. We're going to throw out the negative one because in a real world problem, time cannot be negative. So 7.62 seconds after the ball is launched, it should hit the ground. Now, the table shows the number of hospital visits in millions for selected years. In the table, 99 represents 1999, 100 represents 2000, etc. Determine the quadratic model for the data. Well, this one's going to be calculator intensive. All right, you can do what's called a quadratic regression. We're not really going to do these in class because you're not going to be allowed a graphing calculator. But what you do depends upon your calculator. And so look at the manual of your calculator to do a quadratic regression on the data. It should spit out an answer that looks like this. Y is ax squared plus bx. A is 0.205. B is negative 29.91. And C is 15.34. And you read that as you literally plug in the A, B, and C values. Now use this model to predict the number of visits in 2014. So 2014 corresponds to an x value of 114. So we substitute in 114 into your equation. You get about 811 million. And you can actually verify that with your calculator. Again, your test will be non-calculator, so